Okay, imagine this. You're trying to find, like, the ultimate instruction manual for reality.
Yeah, not just bits and pieces.
Right, not just how stars move or how tiny particles bounce around, but one single, hopefully elegant set of rules that explains absolutely everything.
And that's really the core of this huge quest in physics, isn't it? The search for a theory of everything.
A TOEI.
A TOEI, exactly. And fundamentally, it's about bringing together the basic ways things interact in nature. We usually talk about four fundamental forces.
Right, the big four. Gravity.
Yep, gravity, electromagnetism, and then the two nuclear forces, the strong and the weak.
But here's the kicker, right? The universe, or at least how we understand it now, seems to run on two completely different operating systems.
That's a great way to put it. We've got one language for the really big scales and a totally different one for the incredibly small.
And that's the crux of the problem.
It really is. So on one side, you've got general relativity, Einstein's theory.
His masterpiece.
Absolutely. It describes gravity just beautifully, explains why apples fall, how planets orbit, even the large-scale structure of the entire cosmos.
And it tells us gravity isn't really a pull, it's more like the shape of space and time itself being warped by mass and energy.
Precisely. Smooth, continuous space-time.
Okay, then on the other side.
You've got the standard model of particle physics. Now, this is our super successful theory for the microscopic world.
The world of quarks, electrons, neutrinos, all those fundamental bits.
Exactly, and the forces between them. So, electromagnetism, the strong force holding atoms together, the weak force involved in radioactivity. It covers those three forces incredibly well.
So where's the conflict? They both work brilliantly in their own domains.
But the conflict arises when you try to make them talk to each other. General relativity sees gravity in space-time is smooth, like a rubber sheet.
Okay.
But the standard model operates in the quantum realm, which is fundamentally, well, lumpy. It's based on discrete units, probabilities, jumps, not smooth at all.
Like pixels versus a smooth painting.
Sort of, yeah. And they become mathematically, fundamentally incompatible when you push them to the extremes.
Like where?
Think about the very center of a black hole. General relativity predicts infinite density, a singularity. Quantum mechanics has trouble with infinities, or think about the very first instant of the Big Bang.
The whole universe crushed into a tiny point.
Exactly. You need both gravity and quantum mechanics to describe that, but when you try to combine our current theories, the math just falls apart. You get nonsensical answers, infinities popping up everywhere.
So our two best theories break down right where we need them most.
That's the heart of it. We need to somehow merge the physics of the vast cosmos governed by gravity with the physics of its tiniest quantum constituents. That's the grand unification challenge.
Okay, so for this deep dive, we're going to use the sources you've brought together to really unpack this whole quest, where we are now, the big puzzles, and, well, the really ambitious ideas physicists are chasing to find that ultimate code.
Sounds good. And maybe we should start by digging into the standard model a bit more, because it really represents the high watermark of what we do know.
Yeah, absolutely. I mean, it's easy to focus on the problems, but it's a staggering achievement in itself.
It truly is. Think about it. It predicted particles like the Higgs boson years before it was found.
Which was finally confirmed in, what, 2012? Huge news.
Huge. And that's just one example. It describes this whole zoo of fundamental particles, quarks, leptons, gauge bosons, and how three of the four forces work at that level. It's been tested and verified in countless experiments.
It's like this incredibly precise machine for understanding the subatomic.
You could say that, a brilliant piece of scientific work.
But you mentioned earlier, it's like a symphony missing its final movement. So what's missing? Besides the obvious incompatibility with gravity.
Well, gravity is the elephant in the room, definitely. The standard model just has no place for it.
No.
It doesn't describe it, doesn't include the graviton particle that might carry it, nothing.
Okay, so gravity's out. What else?
Well, there are some major cosmic mysteries it just draws a blank on.
Ah, the big unknowns out there in the universe.
Exactly. Like dark matter, we know it's there. Its gravity holds galaxies together, makes up something like 27% of the universe's mass energy budget.
But the standard model doesn't have a particle that fits the bill.
Nope. Not a single particle in the model has the right properties to be dark matter. Then there's dark energy.
The reason the universe's expansion is speeding up.
That's the one. Accounts for almost 70% of the universe. Even more mysterious in some ways. And again, the standard model. Nothing to say about it.
Wow. So our best theory of fundamental particles is silent on 95% of the stuff in the universe.
Pretty much, yeah.
Yeah.
It's humbling. And there's more.
Go on.
Remember neutrinos, tiny, ghost-like particles. The original Standard Model predicted they should be massless.
But we found out they do have a tiny mass.
Exactly. Which means the model needs tweaking, but it doesn't naturally explain why they have mass or why it's so incredibly small compared to other particles.
Another puzzle piece that doesn't quite fit.
Right. And one more big one. The matter-antimatter asymmetry.
Why is there so much stuff matter and hardly any antimatter?
According to our understanding of the Big Bang and the Standard Model, matter and antimatter should have been created in almost perfectly equal amounts. They should have annihilated each other, leaving mostly energy.
But clearly that didn't happen. We're here.
We are. The Standard Model allows for a slight asymmetry, but not nearly enough to explain the universe we see, which is overwhelmingly matter.
Okay, so gravity, dark matter, dark energy, neutrino masses, matter asymmetry. Quite a list.
And one more thing, which hints at its non-fundamental nature. It relies on about 19 numbers constants.
What kind of constant?
Things like the mass of the electron, the strength of the electromagnetic force, stuff like that. These values are just plugged in. We measure them experimentally and put them into the equations.
They don't comment to the theory itself.
No. A truly fundamental theory of everything, many physicists hope, would actually predict these values, explain why they are what they are.
So the Standard Model is like having a brilliant recipe, but you don't know why you need exactly that amount of each ingredient.
That's a good analogy, yeah. It works, but it doesn't explain the why behind those specific quantities.
This whole situation, this search for a deeper unity, it really echoes what Einstein was trying to do later in his career, doesn't it?
Oh, absolutely. Einstein was never comfortable with quantum mechanics. But even before that, he was bothered by the separation of forces. He spent the last decades of his life searching for a unified field theory.
Trying to weave gravity and electromagnetism together.
That was his initial focus, yes. He felt deeply that these fundamental aspects of nature should be part of a single mathematical structure. He didn't succeed, and the discovery of the strong and weak nuclear forces made the problem even harder.
But that dream, that drive for unification, it's clearly alive and well. Just expanded now to include all four forces.
Definitely. But that fundamental clash we talked about, the smooth versus the lumpy, general relativity versus quantum mechanics, that remains the absolute central challenge.
The conceptual mismatch.
Exactly. It's like one describes reality as this continuous flowing river, and the other describes it as built from tiny, distinct Lego bricks. How do you make those descriptions compatible?
Especially when you need both at the same time, like at the Big Bang or in a black hole.
That's where the theories collide head-on. Trying to apply quantum rules directly to smooth spacetime, or trying to smooth out quantum effects to fit gravity. It just leads to mathematical paradoxes and infinities.
So it's a profound conceptual gap. How are physicists actually trying to bridge it? What are the big ideas being thrown around?
Well, there are a few major contenders, kind of different philosophies on how to tackle it. Probably the most well-known is string theory.
Ah, yes, string theory. The one where everything's made of tiny vibrating strings, not point particles.
That's the essence of it. Instead of thinking of fundamental particles like electrons and quarks as zero-dimensional points, string theory suggests they're actually unimaginably small, one-dimensional loops or segments of string.
Okay, like little violin strings.
In a way. And just like a violin string can vibrate at different frequencies to produce different notes, these fundamental strings can vibrate in different patterns.
And the different vibrations appear to us as different particles.
Exactly. One pattern of vibration might look like an electron, another like a photon, another like a quark. It's the music of the strings that creates the particle diversity we see.
That sounds elegant, actually. How does it help with the big problem, unifying gravity?
That's one of its major selling points. It turns out that among the possible vibration modes of these strings, there's one that naturally has the properties expected of the graviton.
The hypothetical quantum particle that would carry the gravitational force.
Precisely. In most quantum theories, adding gravity is difficult and artificial. In string theory, it just pops out of the mathematics naturally. Gravity is inherently part of the framework.
Okay, that does sound incredibly promising for unification. Wow. What's the downside? Why isn't it universally accepted as the answer?
Well, there are a few significant challenges. The biggest one, certainly from an experimental point of view, is that the mathematics of string theory doesn't seem to work consistently in our familiar 4 dimensions, 3 of space, 1 of time.
It needs more dimensions.
Typically, yes. The most consistent versions of the theory require the universe to have 10 or even 11 space-time dimensions.
Whoa. Where are the extra ones then?
The idea is that they're somehow compactified, curled up incredibly tightly, on scales so small we could never perceive them directly. Think of a garden hose. From far away, it looks like a 1D line, but up close, you see it has a 2D surface.
Okay, I can sort of picture that, but
Uh,
10 or 11 dimensions. And curled up ones we can't see. That sounds hard to test.
that's the main criticism. It's mathematically very rich and elegant, potentially unifying, but finding concrete, testable predictions that could prove or disprove it within our experimental reach has been extremely difficult.
So very beautiful math, includes gravity naturally, but needs extra dimensions that are hard to find. Okay, what's a different approach?
A major alternative is loop quantum gravity, or LQG.
Loop quantum gravity. Okay, what's the core idea there? Does it also use strings or extra dimensions?
No, it takes a radically different approach. It doesn't start with particles or strings. It starts with space-time itself, with Einstein's general relativity, and tries to apply quantum rules directly to the fabric of space-time.
So it tries to quantize gravity directly, makes space-time itself lumpy.
Exactly. LQG suggests that if you could zoom in way, way down past any imaginable scale to the so-called Planck length, space-time isn't smooth and continuous anymore.
What is it then?
It has a granular structure, like it's woven from discrete loops or nodes. Think of it like a fabric. From afar, it looks smooth, but up close, you see the individual threads and the weave.
So space itself comes in minimum possible chunks.
That's the idea. These networks of interconnected loops are sometimes called spin networks. So LQG is focused on the quantum geometry of space and time. It doesn't need extra dimensions, which is appealing to some.
Interesting. So string theory adds dimensions and starts with strings. LQG keeps our dimensions, but makes space-time itself fundamentally discrete. How's LQG doing on the testing front?
It also faces significant challenges in making unique, testable predictions, though perhaps different ones than string theory. Predicting how this granular space-time would affect, say, light traveling across the cosmos is an active area of research.
Okay, two very different paths. Are there other big ideas in the running?
Yes, there's a third category that's been gaining traction, often called emergent theories.
Emergent, meaning things like gravity or space-time aren't fundamental at all.
Precisely. The idea is that what we perceive as space-time and the force of gravity might not be the basic building blocks of reality. Instead, they might emerge from some deeper underlying system, possibly related to quantum information or entanglement.
Okay, unpack that a bit. How can space-time emerge?
Well, think about temperature and pressure in a gas. They feel like fundamental properties, right? But we know they actually emerge from the collective motion of trillions of tiny atoms or molecules. Temperature is just average kinetic energy.
Right, a macroscopic property from microscopic behavior.
Exactly. So, emergent theories propose something similar for gravity and space-time. Maybe they arise from the collective behavior of some underlying quantum bits or qubits linked by entanglement.
Are there specific examples of this kind of thinking?
One influential idea comes from the ADC-FT correspondence, sometimes called gauge gravity duality. It's a complex mathematical discovery suggesting a deep connection between theories of gravity and certain types of curved spacetime, anti-de Sitter space, and quantum field theories without gravity living on the boundary of that space.
So gravity in one reality might be equivalent to a non-gravity quantum theory in a lower dimension.
Roughly, yes. It hints that gravity might not be fundamental, but could somehow emerge from a quantum system. Another related idea is entropic gravity, which proposes gravity isn't a force, but more like a statistical tendency related to changes in information or entropy.
Wow, so gravity might just be thermodynamics in disguise.
It's a provocative idea. These emergent approaches are still developing, but they offer a completely different perspective on the unification problem.
It really makes you wonder, with these vastly different approaches, adding dimensions, chomping up space-time, saying gravity isn't even fundamental, are physicists actually closing in on the answer? Or are we just finding more and more intricate ways to describe our ignorance?
That's the million-dollar question, isn't it? Or maybe the trillion-dollar question. It's something debated constantly. Are these different theories converging or just exploring different mathematical possibilities?
And maybe the answer lies not just in the physics, but in the mathematics itself. This idea that math isn't just a tool we use.
But it might be the fundamental language, or even the source code of reality. It's a powerful, almost philosophical idea that resonates with many physicists.
Especially when you look at things like fine-tuning.
Absolutely. The fine-tuning puzzle is a huge motivator for seeking deeper explanations.
Remind us what that is again.
It's the observation that many of the fundamental constants of nature, the strength of gravity, the mass of the electron, the cosmological constant related to dark energy, seem to have values that are incredibly precisely set.
Like if they were just slightly different.
If they were just a tiny bit different, the universe would be radically different.
Hmm.
Stars might not form, or they might burn out instantly. Atoms might not be stable. Life as we know it certainly wouldn't exist. It looks to some like the universe is tuned for complexity in life.
Which seems improbable if the values were just random.
It does seem improbable.
Mm.
Now, one perspective is the anthropic principle.
Which basically says, well, of course we see a universe tuned for life, because if it weren't, we wouldn't be here to observe it.
Exactly. It suggests there might be many universes, a multiverse with different constants, and we just happen to live in one where the constants allow observers to evolve. It's a possible explanation, but it's not satisfying for everyone.
Because it doesn't really explain why the constants have the values they do in our universe.
Right. Many physicists hope there's a deeper reason, rooted in physics itself. Maybe a theory of everything will reveal an underlying mathematical principle or symmetry that requires these constants to have the specific values we measure.
Like the constants aren't arbitrary inputs, but necessary outputs of the fundamental theory.
That's the dream. This is what drives the search for things like supersymmetry, a hypothesized symmetry linking matter particles, fermions, and force-carrying particles, bosons.
Which could potentially solve some theoretical problems and maybe even constrain some constants.
Potentially, yes. Or grand unified theories, GUTs, which aim to show that the electromagnetic, weak, and strong forces were actually unified into a single force at the incredibly high energies of the very early universe.
So finding these deeper symmetries could be the key to unlocking why the universe has the properties it does.
It could be. It fuels this feeling that maybe the universe isn't just a random collection of laws and particles, but has a deep inherent mathematical logic, that it kind of wants to be understood through numbers.
Which leads to a really fascinating modern question. If the universe is written in math, could a non-human intelligence help us read it? Could AI crack the code?
The role of artificial intelligence. This is moving from science fiction into actual scientific practice now.
Really? AI is being used in the hunt for fundamental physics.
Oh, yes. Especially techniques like machine learning and a specific type called symbolic regression.
How does that work? What are they actually doing?
Well, researchers are feeding AI systems massive data sets, results from particle colliders, astronomical observations, complex simulations of quantum systems.
Yeah.
And the AI's job is to sift through it all and find patterns, correlations, or even underlying laws that humans might have missed.
Like finding a needle in a cosmic haystack of data.
Exactly. Or finding a hidden equation. There's this project called AI Feynman, for example.
Named after the famous physicist Richard Feynman.
Right. And they basically gave the AI data from simulated physics experiments without telling it the known laws, and the AI was able to rediscover many fundamental equations, like Newton's second law, EFMA, just by analyzing the data patterns.
Wow. So it can deduce the equations from the raw number?
It can suggest mathematical relationships that fit the data, sometimes ones that are quite complex or non-obvious to human physicists.
That's incredible. It makes you think. Our human brains evolved to, find food and avoid predators, not necessarily to intuitively grasp 11-dimensional superstrings or quantum foam.
That's a very valid point. Our intuition is based on the macroscopic world.
So could AI, with its ability to process mind-boggling amounts of data and spot incredibly subtle mathematical patterns, maybe see connections or symmetries that are just beyond our biological capacity to grasp easily?
It's a profound possibility. Could AI help us leapfrog generations of theoretical struggle? Could it propose the key equations for a theory of everything, even if we humans then need time to fully understand the why behind them?
Will the final theory be discovered or generated?
That's a fascinating way to put it. It raises questions about the future nature of scientific discovery itself.
Okay, let's try and pull these threads together then. We started with this fundamental clash between our theories of the big gravity and the small quantum.
Right, general relativity versus the standard model.
We saw the standard model is amazing, but incomplete, leaving out gravity, dark matter, dark energy, and other puzzles.
Which led us to the major attempts at unification. String theory with its extra dimensions and vibrating strings.
Loop quantum gravity, quantizing space-time itself, making it granular.
And these newer ideas about emergent gravity and space-time, perhaps arising from quantum information.
We touched on the clues hidden in the seemingly fine-tuned constants of nature and the search for deeper mathematical symmetries.
And finally, this intriguing prospect that AI might become a powerful partner in deciphering the universe's code.
It really forces you, the listener, to grapple with some huge questions, doesn't it? Like, will we ever actually find one single equation for everything? Is that even possible?
Or is reality perhaps layered in ways that defy a single description? And what would finding such a theory truly mean?
Yeah, does it imply the universe is ultimately just a giant predictable machine running on fixed rules? Or could the final theory reveal something even weirder, more intricate, like that idea of a coded masterpiece?
And the impact, if we found it. What happens the day after? How does it change science, philosophy, our whole sense of who we are and where we fit in this cosmos? It's almost dizzying to think about.
It really is. This has been a deep dive into arguably the most ambitious scientific quest ever undertaken, the search for the universe's ultimate operating instructions.
And it's not over. It's a living, breathing, challenging area of physics right now.
And it leaves us with that really thought-provoking idea from the source material. Maybe that final equation, that ultimate theory.
Maybe it isn't something we have to invent entirely from scratch or find buried in collider data.
Maybe it might already be written in the stars, in the math, or perhaps even in us. Something to keep thinking about as you explore your own understanding of the universe.